Morning, everybody. Once again, I apologize for having to run class online this way. Again, unfortunately, my son's school is closed due to the smoke. So today we're going to take a look at section 5.2 and section 5.3. That's the limit definition of the derivative and the power rule. We're going to spend a little time talking about the limit definition of the derivative and most of our time focusing on the power rule. In a normal year, we would have spent an entire day on the limit definition. I was already planning for us not to spend an entire day on the limit definition because we were doing this all online, so this kind of fits right in step. Now, first two things, very important definitions. You're going to hear these definitions over and over and over and over again for the rest of this year. The derivative is a function that determines the slope of the tangent to a curve. In the same way that we're used to thinking, I could have a function x squared plus 5x plus 4, and that function would represent a parabola and all the possible points on it by substituting in an x-coordinate to find a y-coordinate. Its derivative, something we call f prime of x, which in this case would be 2x plus 5, tells us all the potential slopes of all the potential tangents to the graph throughout the graph. Essentially, if I've got a parabola, I could draw a tangent that touches that parabola at only a single spot, not unlike the tangents you would have learned about in geometry, and this equation would get me the slope of that tangent. The numeric derivative just goes the one step further and is the derivative at that location. So if I had a function g of x equals x cubed minus 8, its derivative would be 3x squared, and if I wanted to know the slope of the tangent at, let's say, 4, or in other words, if I wanted g prime of 4, I would simply substitute 4 in to the derivatives equation, and now I know the slope of the tangent when x equals 4. You've already started to see some of the notation that exists for derivatives in those previous two examples I just did. If we're given plain old function notation, f of x, g of x, h of x, its derivative is represented with a dash, kind of looks like an apostrophe, but it's read as f prime of x. If a function is labeled y, we can use y prime notation, and that's the notation a lot of people like to use. The more formal notation when we're just given y is dy dx, and this is simply said dy dx. Now, if you think about what the derivative represents, it represents the slope of the tangent. And for some people, seeing dy over dx makes them start thinking of delta y and delta x, change in y, change in x, and that hopefully should make a little bit of sense because delta means change. Now, for the numeric derivative, we could be given f of x and then be asked for f prime of a, where a is just some number, and that's telling us that we need to find the derivative of f and then plug in a. We could be given y and ask for dy dx at x equals a, which is basically asking us to do the exact same thing, find the derivative of y, and then substitute in that value of a. Not probably going to use that notation all that much. Probably more commonly, if I give you a, I'll ask you for y prime of a. Now, the limit definition of the derivative. This is what makes all of this true. And like I say, in a normal year, we would have spent an entire day just working on this definition, that the derivative of f of x is the limit as h approaches 0 for f of x plus h minus f of x all over h, where h represents the difference in x values. Basically, it's the idea that if I want to get a tangent, I've got to have two x coordinates that are extremely close together. In fact, if h represents the difference of how close they are together, I want that difference to approach 0. I want that difference to get so small it's essentially nothing, and then I actually end up with a tangent. Now, a couple more notations for the derivative. D dx with a bracket or capital D sub x with a bracket, and that simply means that you want to find the derivative of what's inside that bracket, and you'll see what I mean in a few examples. Now, our first derivative rule. I've written down 4 separate functions and their derivative. And if you want, you might even want to try and pause the video at this point to see if you can figure out what that derivative rule is. So I've got 3x squared plus 5x plus 6 for my first function. the derivative of 3x squared is 6x, the derivative for 5x is 5, and the derivative for 6 is 0. Or in the second piece, I've got y equals negative 4x to the 8th plus 7x to the 5th. The derivative for negative 4x to the 8th, negative 32x to the 7th. The derivative for 7x to the 5th, 35x to the 4th. Or my d dx of 5x cubed plus 7x squared minus 8. My derivative for 5x cubed, 15x squared. My derivative for 7x squared, 14x. My derivative for 8, 0. And then finally, for g of x, my derivative for negative 8x to the 5th, negative 40x to the 4th. My derivative for negative 6x cubed, negative 18x squared. My derivative for 7x, just 7. And my derivative for 1, 0. You might be able even to predict what this power rule is going to be. And so when we actually take a look at our formal definition, the power rule says the derivative of ax to the n power is a times n, in other words, coefficient times exponent, and then exponent minus 1. And if you've noticed from those last few examples, the derivative of a constant is 0. No variable means derivative equals 0. Now, a common set of instructions that are going to ask you to find the derivative are things where it's going to say differentiate. It's like when we say add or sum, or we say multiply, or we say product. It's just another term that tells us we need the derivative. And so I use my notation. The derivative of f of x is f prime of x. 12 times 4 is 48. 4 minus 1 is 3. 5 times 2 is 10. 2 minus 1 is 1. Most people aren't even going to bother to write that there. And similarly, our derivative for negative 8 is 0, but most of you aren't going to bother to write that. My derivative for y. Derivative of negative 2x cubed. Negative 2 times 3 is negative 6. 3 minus 1, is 2. 5 times 2 is 10. 2 minus 1 is 1. Negative 6x times 1 would be negative 6x. 1 minus 1 would get me x to the 0. And then the derivative for 10 is 0. Now, since x to the 0 is just 1, we wouldn't even bother to have that value there. We're not going to see much more work, or much of a difference, I should say, when we have to find the numeric derivative, what's f prime of 3 in this case. We just have to go a step further. So my derivative of my given function, 2 times 2 is 4, 2 minus 1 is 1. Derivative of 6x, 6 times 1 is 6, 1 minus 1 is 0, and then the derivative of negative 8 is 0. Like I say, we now just go one step further and substitute in 3, and my numeric derivative is 18. The slope of the tangent when x equals 3 would be 18. Slope of x equals 3 is 18. And similarly, we're not going to see anything different in this last one. I'm going to use my power rule. So I've got negative 12x squared minus 6x minus 5. I'm going to substitute in my negative 1. I'll end up with negative 12 plus 6 is negative 6. Negative 6 minus 5, negative 11. And so, like that last one, I'd be able to say the slope of the tangent when x equals negative 1 is negative 11. All right, I know this is a brief tutorial. Hopefully it's helpful. We are going to spend another day on Monday talking about the power rule, so if it's a little odd at first, don't worry. We're still going to be working on this come Tuesday. All right. Your homework is on Power School. Here's your homework here. Use the power rule in all of the problems. I do not expect you to use the limit definition or the numerical definition. Okay, I expect you to use the power rule. All right, good luck, and I will see you Tuesday.